We will continue our discussion on the properties of homography or projective transformation. Now, we will look at the properties of conics, how they appear in the transformed space. So, earlier we discussed about the general representation of a conics in a non-homogeneous coordinate representation. The conics are represented in this form, whereas in a homogeneous coordinate representation we can represent it in a simple quadratic structure x transpose C x equals 0, where C is given by these parameters. It is a symmetric matrix, it is a 3 cross 3 symmetric matrix, and as you can see that there are 5 independent parameters, because C is also an element of the projective space. So, if I multiply C with a scale k, if I multiply C with a scale k, still it will remain the same conics. And another interesting property of this conic is that there is a dual conic, dual representation of this same conics. It is a representation by their line tangents. So, take any line tangent given by L, that should satisfy also this property, where C star is the dual conic representation, and that is given as C inverse. We have discussed all these properties in our previous lectures. So, let us see how a conic goes under transformation, how a conics appear. So, let us consider a transformation H, where a point x is transformed to x prime. So, all the points which are lying on a conics and which are given by this equation x transpose C x equals 0, let us see that in the transformed space what property they follow following the conics rule. So, we can write this equation x transpose C x in this form, because x is replaced by H inverse x prime. This is coming from here. So, x equals H inverse x prime. So, if I replace it, then I get this equivalent form, and we expand this equation once again. That means, these transpose operations can be expanded on the matrix multiplications, which is x prime transpose H minus T C H inverse x transpose. So, you can see here there is a quantity H minus T C H inverse. So, it is a matrix multiplication, it is a composite, it will provide you another matrix, and say let me write this matrix as C prime. Now, this is also a 3 cross 3 matrix, and you can find out that now even in the transform space you have a matrix 3 cross 3 matrix which is in this form and which satisfies this equation, and this is nothing but again another conics representation. So, we get this particular. So, the transformed conics is given by this H minus T C H inverse H minus 1. So, a conic remains a conic under homography. That is the essence of this particular mathematical exercise. So, conics is an invariant in this sense after transformation. Even the dual conics, because the dual conics is nothing but the inverse of the conics in its point representation. So, if I perform the inverse operation, so I will get its corresponding dual conics, and that is consistent enough with respect to these transformations. There is another interesting property of this transformation, particularly in the conics there is an interesting property of conics. So, there are 2 points which are known as circular points. These points we have already mentioned while discussing about the invariances of similarity transformations. We have seen that these points are invariant under similarity transformations. So, the circular points, the definition of the circular points are given here. As I mentioned that in this representation you need to consider a 2-dimensional projective space with a complex representation where one of the axis is the imaginary axis, other axis is real axis, and there is a scale axis. So, these are the 2 points, and if I apply a transformation, once again you get a representation in the complex space itself. And under conics we have already discussed also this, that under similarity transformation these points they still remain the same. So, they are the fixed points of similarity transformation. And this is a summary of this particular property, that the circular points are fixed points under the projective transformation H if and only if H is a similarity, and also they are also on line at infinity, because you note that their scale, this third dimension is their third dimensional value or scale value is 0, which means if I apply the point containment relationship with the line at infinity, it will satisfy that relationship, which means the dot product of the column vectors represented by circular points and line at infinities, they should be equal to 0. Just to elaborate this part. So, if I perform this operation 1 I 0 and 0 0 1, so that should be equal to 0, which is the point containment relationship. So, every circle intersects line at infinity at I and j. That is another property of circular points. Every circle. So, let us elaborate this part. So, you consider a representation of a circle in the homogeneous coordinate system. So, this is a representation of a circle. You can see that x 1 square x 2 square, where the coefficients of x 1 square x 2 square they remain the same. In this case, we have normalized it with respect to those coefficients, and then this is a representation of the. So, these are the parameters for a circle. You require only 3 parameters d, e, f, and that is the representation of the circle. And here if I set the value x 3 equals 0, if I set the value x 3 that is equals 0, which means that you are computing the line at intersection of line at infinity, because any point whose x 3 coordinate, which is the third coordinate is 0, that is lying on at the line on line at infinity. So, if I set x 3 equals 0, so these are the values would be equal to 0, these are the components will be equal to 0, and finally, the equation would be x 1 square plus x 2 square equals 0. And you can note that these 2 points I and j, they satisfies this equation, because if I take for I, that means 1 square plus I whole square, which is 1 minus 1, that is equals 0. So, which means the circular point I, it is lying on the circle and also it is lying on the line at infinity. So, that is why the every circle intersects this property, every circle intersects line at infinity at I and j. So, this is also another interesting property of circular points. So, since we have these 2 circular points, now we can define also conic duals, and we have discussed about this dual representation of conics previously also. By using 2 circular points, we can define a degenerate conic So, we can define a degenerate conic in this form. You can see that this is a 3 cross 3 form, and which will be eventually in a simplified representation which will look like this. So, you have 1 0 0 0 1 0 0 0 0. This is a typical dual conic formed by the two circular points, and this dual conic has a very interesting property. Since the circular points are fixed under similarity, this dual conic also remains fixed under similarity. So, this is another interesting feature, and this is just a derivations. Earlier also we mentioned that circular points are fixed under similarity, and so the dual this dual conic representations, dual to the circular points, and these dual conic representations using circular points, that is also fixed under similarity. And degree of freedom of transformed this dual conic at infinity, that is 4, and its determinant is equal to 0. That is another property of these dual conics. And other thing is that the line at infinity is a null vector of this dual conic at infinity, because if I multiply the dual conic at infinity, that is the way we can call it. If I multiply with the line at infinity, you will get a 0 here. That means a 0 vector, which means it is 0 0 0. Let us discuss how an angle could be measured under homography. Suppose we have two straight lines as shown in the figure, L and M, which makes an angle theta, and their directions of the straight line are given by L1 L2 and M1 M2. In the projective space we have this 3 vector representation, but we know that first two components of that 3 vector they provide you the corresponding direction ratios. So, they could be used for measuring the angle between these two straight lines, as shown in this expression, that if you take the dot product of these vectors L1 L2 and M1 M2, and then if you normalize them, basically dot product of unit vectors representing those two directions, then you will get cosine of the angle, that is cos theta. Now, interestingly, we can see that in fact this measurement can be also done even under homography. There is an invariance which gives you this flexibility. So, let me discuss this property here. You can see that even under homography, this product remains, I mean cos theta can be expressed using the dual conic at infinity in this form. That means, if I take L transpose C infinity star M in the numerator, that expresses L1 M1 plus L2 M2. Note here that C infinity star is the dual conic at infinity, and it is given by this 1 0 0 1, and these are all zeros. So, once you multiply L1 L2 L3 L transpose L transpose C infinity star M is L1 L2 L3 and then 1 0 0 0 1 0 0 0 0, and then for M we have M1 M2 M3, and if I multiply it should give me L1 M1 plus L2 M2, which is the numerator of this expression. Similarly, L1 square plus L2 square can be computed in the same way, L transpose C infinity star L, and M1 square plus M2 square, this can be computed as M transpose C infinity star M. So, this is this is what it is computing the same quantity, but the interesting part is that there is an invariance associated with this measure. In particularly this product L transpose C infinity star m, even if I perform homography, corresponding lines and corresponding dual conic, transform dual conic at infinity in the homography, under homography, they also preserve the same quantity. So, let me explain that. So, this is invariant under homography, and we use this property where the relationship between dual conic at infinity under transformation of homography H and with the dual conic at infinity in the original space is given by this. And as you know that the line after transformation also they are related, transformed line and the original line in the original space, they are related by this. So, if I replace these quantities, so let me show you the derivation. So, in this derivation we can see that we are, so this remains actually this remains the invariant. So, L prime, which is the transformed line in the under homography, it becomes now L transpose H inverse, and then C infinity star or dual conic under transformation, dual conic under transformation becomes this, and then this is the transformed line, this part is transformed line. And as you know that H inverse H, it would be identity matrix. Similarly, H transpose and inverse of H transpose, they also form identity matrix. So, what you essentially gets that this is equal to L transpose C infinity star m. So, this is how this becomes an invariant. So, the measurement of cos theta, the same expressions, even if I use this in the transformed space, that means if I use all the corresponding transformed lines, transformation of dual conics, transformation of corresponding lines, then also we will get the same measure cos theta. That is how it becomes invariant. So, once this is obtained, so what you require to do that given a image under homography, you would like to find out, like to compute the transformed dual conic at infinity, dual line conic at infinity, that C infinity star prime. And if you can obtain that, then you can use this relationship to obtain the original angle formed by those two lines in the original space, which means suppose there are two perpendicular lines in the original space, and even after transformation under homography they will not remain perpendicular, but this relationship will still remain, and as you know the cosine of the angle between these perpendicular lines, that is equal to 0. So, we can always say this orthogonality property of two lines, they are preserved under this using this dual conic, dual line conic at infinity in the transform space. So, let us consider this. Here I would also note that this relationship we can have L prime and also M prime. This should be considered that it is L prime transpose C infinity star prime and M prime, all the quantities are in the transform space, then actually that should be equal to 0. So, this could be used for as I told you that for measuring angle, and in fact for recovering metric properties, as we can explain in the next slide. So, first what we need to do, we need to estimate the this C infinity star prime, that means the dual line conic under transformation at infinity, dual line conic at infinity under transformation, and we will be using this property of orthogonal lines, which means I would consider that those lines, these are transformed lines. So, L prime transpose C infinity star prime and M prime, that should be equal to 0, and that would give me in this way that would give me an equation. So, since there are, as we know that there are 5 parameters, independent parameters in the conics. So, minimum 5 such orthogonal pairs are needed, so that you get 5 different equations to solve it. So, a typical equation will look like this. So, you consider a particular line, say L and M. We can consider L and M itself in that space. So, there is no problem in notation, it is a notational description only. So, you will be using this equation. So, L is represented as L1, L2, L3, M is represented as M1, M2, M3, and you can observe that an equation L transpose C infinity star and M transpose, this expression will be like this, but C is given, C is a general conic here. So, I will be estimating this, and I am replacing by the corresponding conic variable C, and which is represented by the parameters A, B, C, D, E, F, which means I can write C as a vector, column vector A, B, C, D, E, F. These are the parameters, and C can be represented as a symmetric matrix using those parameters. We have discussed earlier how C can be represented using these parameters. So, you have to obtain these parameters using these equations, but as you can see that there are 6 parameters and there are 5 equations, and in fact, it is a set of homogeneous equation. So, you need to use the method what we have used earlier for solving set of homogeneous equations. We can apply the direct linear transform method to solve a set of homogeneous equations to get C, and which means that if I express it in terms of matrix, say set of 5 equations. So, in this way I can represent the set of equations as a matrix multiplication, where each row of A is formed by this particular row for every pair of orthogonal lines, and if there are 5, there will be 5 such rows. If there are more, there will be more rows, and you have to use an least square method. So, you have to minimize these norms subject to the norm of C is equal to 1. So, that is the problem statement in this context we have already discussed, and we know that solution of this particular set of equations would be that you have to take the corresponding eigenvector of A transpose A. So, the eigenvector of A transpose A which has the minimum eigenvalue. So, that would be the solution of this C of this matrix. Otherwise, you can also convert it into a set of non-homogeneous equations when you are working with exactly 5 equations. So, set F equal to 1, once again still that limitation is there. Suppose F is 0 in the representation of conic, then this will not work, but let us assume that we can work with some non-zero F in your particularly given problem. Then you can use also non-homogeneous set of non-homogeneous equations, and you can use inversion by putting the values of F at the right hand side of the equations. We have discussed all these methods. So, in using this kind of technique, you can estimate the conics and also estimate the dual conic at infinity, dual line conic at infinity, and then we need to do this operation, because as we know that dual line conic at infinity, it is a rank deficient matrix. So, it should be rank 2 matrix. So, what we do, the trick what we can perform here, that we can do the singular value decomposition on C and take the set the minimum singular value as 0. So, let me explain this also. Suppose you get a C and you perform the singular value decomposition. We know singular value decompositions of C can be represented in this way, where D is a diagonal matrix and its singular values are given lambda 1, lambda 2, lambda 3, and these are all 0 submatrices, these are all zeros, that is D, and U is a 3 cross 3 matrix and also B transpose, that is also 3 cross 3 matrix. So, what we can do, we can set lambda 3 equal to 0 and suppose lambda 1, it has been rearranged in that way, lambda 1 is the maximum, then lambda 2 and then lambda 3. So, set lambda 3 equal to 0 and then use that modified 1 as your estimate. So, use E D V, where D tilde is the diagonal matrix, while lambda 3 is set to 0. So, that is how you can make it a rank 2 matrix. So, in this way you can compute, you can estimate the dual conic at infinity or dual line conic at infinity and in the transformed space. Now, using this you can perform a metric rectification that I was mentioning. So, let us discuss that part also. So, how we can recover the metric properties? So, what we require to do now, we need to estimate the homography from C infinity star, and that is up to similarity. We have seen that this under the similarity transform this dual line conic remains preserved. So, whatever we can do, we can that homography can be multiplied by any similarity homography, it will still remain the same, the properties will remain the same. So, let us consider up to similarity we will be computing this matrix, which means the ratios of the distances between edges, those will be preserved, not the exact distance that you can estimate in this way. So, we can use matrix decomposition method to compute the homography, which means I need the homography matrix in such a way that I should get the transformed dual line conic what we have estimated, dual line conic at infinity, and note here this C infinity star is the dual line conic at infinity, and which is given by this particular matrix. So, if I can decompose this matrix in such a way that we have this in this form, and at the middle of this matrices, 3 matrices, you have a matrix like this, then this could be an homography. So, one such example, one such method could be like this. That means, since this is a symmetric matrix, because conic is a symmetric matrix, we can decompose in this way. We can adjust the singular values in such a way that these two quantities would be 1 1, and accordingly the vectors in U and U transpose columns of U would be adjusted. So, now you see that if you use this kind of decomposition, it is a singular value decomposition exactly what we did, but the diagonal matrix has to be adjusted in such a way that both the singular values becomes 1, accordingly columns of U's should be adjusted. So, as you see, the middle one satisfies the structure of a C infinity star or dual line conic at infinity, and then we can take U as the homography, and we can apply the inverse of this homography to the image to get the rectified image, or to recover the metric properties. As I mentioned, you can get the ratios of the distances. So, with this let me conclude this lecture and also this topic particularly with this summary, that we have studied various transformation under homography, like we studied how a point could be transformed into another point in the transformation space. In the transform space, how they are related? They are related by a non-singular 3 cross 3 matrix, and which is called the projective transformation. It preserves the collinearity of the points in the transformed space. It is invertible, and correspondingly a line is also transformed into another line in the transformed space, and the relationship between the transformed line and the original line is given by this L prime equals H minus T L, which is transpose of inverse of the transformation matrix. Then the conics, they remain conic after transformation, and their relationships have been summarized here. Similarly, the dual conics representation also is valid in the transformation space, and projective transformation, they form various groups. They form a group, so that is a projective linear group, and there are different subgroups and their hierarchy that we have discussed, like we have discussed about projective linear group having 8 degrees of freedom, then affine group having 6 degrees of freedom, and then Euclidean group having 4 degrees of freedom, and oriented Euclidean group having 3 degrees of freedom. Incidentally, Euclidean group is a similarity transformation what we discussed, and oriented Euclidean group, one of them is a isometric transformation as we discussed. Then we discussed about conic dual to the circular points, and we have seen its various interesting properties, like first thing, it is invariant under similarity transformation. Then line at infinity is a 0 vector of this particular conic dual. It preserves cosine of angle of two lines under transformation. That is interesting. So, I should say using the transformed dual conic, you can compute the cosine of these angles. It implies that. So, this is a particular property how cosine of angle could be computed using the transformed dual conic, and homography is used in various tasks. Some examples are given here, like you can use homography for rectifying images. There are two types of rectifications we discussed. One is affine rectification, the other one is stratification, which helps you recovering the metric properties, particularly proportionate distances that you can compute, that you can recover under performing that corrections. So, with this, let me stop my lecture here, and thank you for listening to my lecture. We will continue our discussions on other topics from next lecture. Thank you very much.